Good morning. It is morning here, and I want to talk to you about Math 433. And the last time we talked, we had talked about the exponential distribution. I want to start by doing a little more work with the exponential distribution. Very interesting assignment was problem 6.16, page 208, which is talking about an exponential distribution's lack of memory. So think of it this way, if you would. Suppose that I've got, let's say, an electronic component. Maybe it's a computer chip. And its lifetime, that is, its time to failure, is governed by an exponential distribution with a fail rate of alpha equal 0.01, meaning in an hour, the average would be 0.01 or 1/100th failure. So the average lifetime would then be, the reciprocal of that would be 100 hours. Okay, so that's what we're talking about. Now in this exercise, we're asked to show that the probability that X, that's the time to failure, is greater than or equal to T plus T, so that's some time value. And I didn't want to put a parentheses there. I wanted to put a slash. Given that X is greater than T is equal to the probability that X is greater than T. Now, at first glance, that just maybe looks like a confusing bunch of symbols. Since X is continuous, it really doesn't matter if I have less than or equal to, greater than or equal to, greater than, less than in there. So, but I will change it to look like that. What's this telling us? It's saying that if the component has already lasted T hours, what's the probability that it will last lowercase t more hours? Given that it's already lasted T hours, what's the probability that it will last T more hours? And this result asserts that it's the very same as the probability that it will last lowercase t hours the first time you turn it on, which means that the process has no memory. Let's just see if we can prove that. Now, you're going to need to remember some elementary probability theory, and I want you to think like this. The probability of A given B, do you remember what that is? That's called a conditional probability, and by definition, it's the probability of A and B divided by the probability of B. So using that definition, the probability that X is greater than or equal to T plus T given X is greater than or equal to T, I'm going to run myself out of room here, is equal to the probability that X is greater than or equal to T plus T and X is greater than or equal to T divided by the probability that X is greater than or equal to T. Now you have to read that. This is really not a spoken language, and it's too many T's in there. It sounds ambiguous unless you read it, and then it's no longer ambiguous. If you can read it. This is a plus sign, right? Plus. t plus t. So these go together. Okay, now think with me about what this would be. This is the event that x is greater than t plus some lowercase t, and x is greater than or equal to the uppercase t. Well, on a real number line, this is precisely what we're talking about. Here's 0, and this is t, and then we want to go a tiny bit more. Well, it doesn't have to be a tiny bit, but some amount more, like that. And if we do, we arrive at t plus t. So what's the probability that we're greater than this, given that we're greater than this? Well, this reduces to, because the event x greater than or equal to t is a subset of x greater than or equal to t plus t, so it reduces to the probability that x is greater than or equal to t plus t. And then that is divided by the probability that x is greater than or equal to t. Now, let's convert these, I think, to this, using the CDF, the cumulative distribution function. We know that gives us lower tail probabilities. There's multiple ways we can do this, but this is what I want to do. So I would say this is equal to 1 minus the probability that x is less than t plus t divided by 1 minus the probability that x is less than t. Because why? This probability and this probability are complementary. And so the kind of the first law of probability here tells me that 1 minus this probability is equal to that probability, using the same thing in the denominator. Okay. Now, this is equal to 1 minus the integral from 0 to t plus t. And I think we just left this alpha. Alpha e to the minus alpha x dx, and over 1 minus the integral from 0 to t alpha e to the minus alpha x dx. And that's equal to. Now I can break this integral up into two pieces, 0 to uppercase t and uppercase t to the lowercase t. So let's do that. So I'd have 1 minus, we got to be careful of grouping here, 1 minus the integral from 0 to uppercase t, alpha e to the minus alpha x dx, plus the integral from t to t plus t, alpha e to the minus alpha x dx. And that's going to be over 1 minus the integral from 0 to t alpha e to the minus alpha x dx. Okay. Well, let's go ahead and integrate these. And I guess you can integrate these by substitution, can't you? If we let let u be negative alpha x, then du would be negative alpha dx. Maybe I should write that down. So if we're going to let u equal negative alpha x, that's the exponent on the exponential, then du would be negative alpha dx. And an easy substitution, because I've got an alpha that I can put with the dx, and I just need to supply a negative sign. So I'm going to scroll up a bit, and I'm going to make this 1 minus, be careful of the aggregation symbols here, and this would be, if I put a negative out here, it would be, it'd be e to the u du, which is e to the u. And what's u? U is minus alpha x. And so I think this would be the negative that I've got to supply here. And then alpha x, well, e to the alpha x. I want to make sure I didn't make a mistake there. Yeah, between 0 and t, and then I've got a plus in here. Now I'm integrating the same function, it's just the limits that are different. So this is going to be negative e to the alpha x t to the t plus t, and close that up. And then that's over 1 minus e to the sorry, these would still have a negative sign up here also. Negative alpha t, and this would be between 0 and t. Okay, now let's just clean this up algebraically, because we're not doing calculus at this particular moment. So this is going to be, got to be careful of these signs. I think I'll do it this way. 1, now I'm going to drop this big bracket here. And so if I drop the big bracket, I've got a minus here, so this is going to be plus e to the minus alpha x, x between 0 and t. And I've got a minus here, don't I? But I've got a negative out here. And so that's going to be a negative, and a negative is going to be plus. And e to the minus alpha x between t and t plus t. And that's the numerator. And the denominator is going to be 1 minus. Now, I think I made a mistake here. When I integrated this, I probably took this negative and put it on the alpha, because I needed a negative alpha dx. So I'm pretty darn sure that that would be a plus. And I'm a little more than pretty darn sure. That was just a mistake when I wrote that. So this is a 1 plus. And then maybe we'll just go ahead and do this one, since it's pretty straightforward. 1 plus what I get when I substitute t in here. So that's going to be e to the minus alpha uppercase t, and then minus what I get at the lower limit. You would put in a 0 for t, you get e to the 0, which is minus 1. Okay, well, we're not done, but we're getting there. So then what do I have? I've got a 1, this one right here, plus e to the minus alpha t. This thing that looks like a 7 up here was a t. E to the minus alpha t minus what I get at 0. Put in a 0, you get a 1. So minus 1 plus, that's this plus right here, and we're over here now, and I've got an e to the minus alpha t plus t, and then a minus e to the minus alpha, and that's an uppercase T, and that's all over. Well, here's a 1 minus 1, so all I'm left with down here is e to the negative alpha t. Okay, clean up. The cleanup's taking a lot more time than the calculus. So here's a 1 and a negative 1, and so those are gone. And here's an e to the minus alpha t and a negative e to the minus alpha t. And so those are gone. And here's an e to the minus alpha t plus t. So when we multiply base raised to the exponents, we add the exponents. I want to undo that and realize that what I've got here is a t minus alpha uppercase t times e minus alpha lowercase t, and that's over e minus alpha uppercase t equals, well, this one and this one cancel, so it's e to the minus alpha t. Now, what can we tell ourselves about the probability that a component will last more than t hours when I take it out of the box and plug it in? Well, this would equal 1 minus the probability that x is less than t, and this would equal 1 minus the integral from 0 to t alpha e to the minus alpha x dx would be equal to 1. Now I need to take this minus and put it on the alpha and put it with the dx, and so I've got a minus alpha dx, and so I've got a differential that goes with the minus alpha x. This is integration by substitution. You've known how to do this for a long time. And so that leaves me with a plus here and an e to the minus alpha x between 0 and t, which is equal to 1 plus e to the minus alpha t minus 1 equal e to the minus alpha t. So the probability that x is greater than or equal to t is e to the minus alpha t, and the probability of that conditional probability that we started with was e to the minus alpha t, and we see, of course, they're exactly the same. And so we've established that this process has no memory. So that was, well, an interesting observation about random variables that follow an exponential distribution, and a good exercise in Calculus 2 style calculus. And it has an implication for us. You do preventative maintenance to replace a component before it fails. And so if you've got an irrigation pump that's pumping water to your fields, and you don't want that irrigation pump to fail, and you know that the average life of that pump is 100 days, then after 100 days, you might go out, even though that pump is working, you might go out and replace that pump and then take the one that was in service back to your shop and replace the gaskets or impeller or the bearings or whatever it is that tends to go bad in those. That's preventative maintenance to keep the system up, because you know that the probability of getting another 50 days out of that pump are going to be pretty small. But for components like electronic components that would follow, the time to failure would follow an exponential distribution, there really is no sense of doing that kind of preventative maintenance. If I have a component that's lasted 90 hours, what's the probability it will last 50 more? Well, it's the same as if I go get one out of the box and plug it in, and that one will last 50 hours. And so there is no point in doing preventative maintenance if you've got components that actually follow an exponential distribution. Now, another question would be show that it follows an exponential distribution, and you can do that at least approximately by gathering data on a large number of cases and seeing what the distribution of fail times look like. There is other ways. I think I won't take time to do another way, but there are other ways to go over this same exercise that we just went over that show a little bit different manipulation of the calculus and the probability theory. And I think you can find one of those in your textbook, but they get you to exactly the same conclusion. So I don't want to take time right now to do that, but I'd be happy to do it for anybody one-on-one that's interested in that. So, just for the fun of it, I went ahead and simulated an exponential distribution that has an average time to fail. Scroll up. Average time to fail 100 hours. So the fail rate would be equal to 0.01. So what's the probability that the time to fail will be at least 50 hours? Well, one way we could do that would be to follow the life of a large number of the components that have this distribution, a large number, and see what the relative frequency is. So this would be approximately the relative frequency of the time to failure being greater than or equal to 50 hours. Now, that's not going to be easy to do without some kind of technical aid here to help us with this simulation, because we don't have a whole bunch of components that are following this distribution. I mean, in reality, we don't. And if we did, we'd have to sit around for hundreds, thousands of hours to get a large number of failures, or else we'd have to be looking at tens of thousands or 100,000s of these components running simultaneously. In any case, it would be very difficult to calculate the real data, but it's easy enough to simulate this kind of data. So I'm going to share a different screen with you and hope that I can enthuse. Okay, we can start here. This is our studio, and I'm looking on line 132, and I'm defining a collection of values called time to fail, and they're going to be exponentially distributed, and I want 5,000 of them, and I want the fail rate to be 0.01. So these would be the components we're talking about. And I'm just going to grab time to fail for 5,000 of them. And this is, what I was talking about before all the confusion here and how Zoom works. I can, with the aid of RStudio, I can simulate 5,000 components running until they fail in the blink of an eye. Blink, okay, it's done. And then we can take and graph their life. And I'm going to just graph a histogram of their lifetime, the lifetime to fail. And let me just run that for you. And I want to make it a little bit bigger for you. And there it is. Now, the gray here, the histogram, is the observed time to failure. And the blue line is the theoretical time to failure. And so, they've got the same general shape, don't they? This is a distribution we call skewed to the right, because we name the skew by the direction in which the long tail points. And remember, we could calculate the skew if we'd use the moment generating function. That's probably the easiest way to calculate the skew. It'd be the third moment about the origin, wouldn't it? And then we've got to do a little more arithmetic to it, divide by the variance, and multiply by 3. I don't remember. I'd have to look that up. But we would know how to do that. Anyway, this is skewed to the right. And this would be the time to fail for 5,000 components. So it takes only a second to do. Now I want to do this. I want to find out what the relative frequency of these components lasting more than 50 hours is. So on line 136, I'm going to look at each of those 5,000 components. That's the time to fail greater than 50. And if they fail after 50 hours, if the time to fail is greater than 50, I'm going to code them a 1. But if they fail before 50 hours, I'm going to code them a 0. Now, all I have to do is execute this line right here, and it's done for me automatically. I don't have to do it by hand. The next thing I'm going to do on this line is to add up all these zeros and ones. And of course, when you add a 0, it doesn't change the sum. So I'm really just adding up the ones. And that's going to tell me how many of these 5,000 components lasted more than 50 hours. And then if I divide that by how many I had, 5,000 of them, then that's going to give me the relative frequency. So let's do that and see what we get. This tells me that I'm going to round this to 61% of these components lasted more than 50 hours. 61%. Or the probability that the out-of-the-box component will last more than 50 hours before failure, that probability is 0.61. Now, given that they've lasted 90 hours, what's the probability that they'll last another 50? So we'd be looking at components that have lasted 90 plus 50 or 140 hours. And so I'm going to take the components, all 5,000 of them, And I'm going to look and see if they lasted more than 140 hours. If they did, I'm going to code them 1. If they didn't, I'm going to code them 0. I'm going to add up all those 1s and 0s. And as soon as I do that, I will know how many of these components lasted more than 140 hours. Now, we're dealing here with the conditional probability, just like in the problem that we just ran. This is somebody that wants to sell me insurance or make sure my truck is insured. So I'm going to divide by the number of components that have lasted more than 90 hours. And so that's a conditional probability. All right, so let's try that. And the probability that we get is 0.6243. Now, remember what we're doing. I'm comparing these two, and I want to tell you they're just about the same. This is the relative frequency for the 5,000 components that I looked at. So this is not a theoretical frequency, it's an empirical probability. Of the 5,000 particular components that we looked at, there was a 61% probability that one out of the box would last more than 50 hours. Now, of those 5,000, if a component has already lasted 90 hours, what's the probability it's going to last another 50? And that probability is 62%. And this is an empirical verification of the result that we just did using the calculus. And it tells me that these are certainly about the same. Now, if I would do the random simulation and get a different set of 5,000, of course, these numbers would be slightly different because this is empirical probability, not theoretical probability. We could certainly do that computation using R for a theoretical probability. I'd rather not take the time to do that right now. I would invite you to do that with R. I know some of you have R, or of course, or with Minitab, or with SAS, or SPSS, or your calculator. If you've got a TI, I think probably even an 84 calculator will do that computation for you directly, the theoretical computation. And again, I'd be happy to help you with that individually, or if there's multiple of you that are interested, I would be happy to do it for you as a class lecture. The next thing we want to take up is the normal distribution. Normal distribution is certainly one of the most used, if not the most used distribution. I'm going to see if I can get R to jump back to that computation screen without making me hunt for it. And so I want to stop this share, but start a new share of this screen right here. And I don't have much indication, but I got a little bit of indication that that might have worked. So now we want to look at the normal. The normal distribution. And what do we know? Well, everybody knows the normal is the bell-shaped curve. I'm going to do this freehand, but a normal bell-shaped curve would look something like that. So this would be my density function, call it f of x. And in this density function, right under this peaky part, this would be the mean for my normal. And I would have an inflection point about right there, concave down, concave up. And that would be the inflection point. And that would be one standard deviation for this distribution above the mean. And the mean is completely symmetrical. So I could look for the inflection point on the left-hand side, or I could just use this distance right in here and come down that distance, and I'd be right under the inflection point. And this would be mu minus sigma. So that would be a normal distribution. the density function would be f of x is equal to sigma root 2 pi e to the minus 1/2 x minus mu over sigma squared. And we could use R or Desmos or Maple or Wolfram Alpha and graph this function, and we would get a graph that would look like this, except it would be much prettier and more precise. That's the normal distribution. What kind of things are distributed normally? Well, the height of 5th grade girls would be normally distributed, or the weight of 12th grade boys would be normally distributed, or the I keep thinking of height and weight now that I've said height and weight, but the probably the body temperature of a healthy adult, male or female, or probably the well, if we would take 1 acre plots of land and count the number of grasshoppers per acre and do that locally, don't do that in Alaska and Belize, do that all around South Texas, the number of grasshoppers per acre would probably be normally distributed. And early on, Carl Pearson's time, so many things were noticed empirically to have the normal distribution that the distribution got the name normal. I mean, at the time it was given that name, it meant this is how things are normally, usually distributed. All right, but today we mean something, even though, you know, the number of things normally distributed hasn't changed. When we say normal distribution, we mean a random variable that has this probability density function. So that's what we mean by normal, a random variable that has that probability density function. Now, if you'll read your textbook, and I hope you are, if you look on page 211, I thought about doing this with you, but I think you can read it on your own. You'll see step by step a development of the evaluation of that integral where the f is the normal PDF. And what would this be equal to? Well, if this is in fact a probability density function, that has to be equal to 1. And the other requirement, if this is in fact a probability density function, is that it's everywhere non-zero or non-negative, everywhere positive. Well, you see, this is an exponential function that's always going to be positive, and this would be a positive constant. We can't variance. The standard deviation is the square root of the variance, and so it's the positive square root. This has got to be positive. So the only thing we'd have to show is that this integral is 1. It's an interesting development. It's not non-tedious, but it's done in great detail for you on page 211 of your text. And then we have theorem 6.6, and that's right around page 211, which tells us that a moment generating function, mx of t, for the normal is e to the mu t plus 1/2 sigma squared t squared. Now at this moment, you think about this symbol symbol sigma just as being two numbers. Don't think of them as the mean and the standard deviation for the normal distribution, because maybe we don't know that yet. We've not established that. So I've got a PDF, here it is, and I've used the PDF and I've calculated a moment generating function. Now let's use the moment generating function to find the parameters for the PDF f of x, that is to find the mean and the standard deviation. It's not all parameters, but we'll find the first two parameters. So how are we going to do that? Well, mu1 prime, so this would be the first moment about the origin. That's the thing we call the mean. And we know that this would be equal to, from previous theorems, we know that this would be equal to the derivative of mx of t dt evaluated at t is equal to 0. So is that the best way to find this creature? Because there are other ways. Yeah, it looks like it's pretty reasonable, because this is not going to be hard to differentiate. So it's an exponential function. So I'm going to have to take the derivative of the exponent. I'm differentiating with respect to t. So I'm going to get mu plus, now this is 1/2 sigma squared, but this 2 will come down. So it's 1/2 times this 2, that's going to be a 1, and then t to the first power. So this 2 and this 1/2 are going to multiply to 1, and I'm going to have sigma squared t to be evaluated at t is equal to 0. And that's equal to, well, 0 times the sigma squared, that gives me a 0. So mu is what I have left. So it turns out that this value in here, this number, actually is the mean for the normal distribution. Now, what can you tell me about finding sigma? Well, the second moment about the origin would be equal to the second derivative of the moment generating function with respect to t evaluated at t is equal to 0. And this is going to be equal to, well, I've got to take the derivative of the first derivative. Actually, it was not thinking ahead on my part. I didn't write down what the first derivative was. I mean, I guess I did. It's, well, no, I didn't. Well, in fact, I didn't even do this right. What a horrible set of mistakes I'm making today. Let me do this right. Okay, so here I want to take the derivative of this function right here. So I certainly started this out right. This is going to be mu plus sigma squared t. But when I say I didn't do it right, I left off the most important part. Like that. And then this is evaluated at t is equal to 0. Well, I mean, I got the right answer, and that's why it didn't jump out at me that I'd made a mistake. Let's evaluate this at t is equal to 0. This multiplier becomes just mu because this t makes this piece a 0. So the multiplier is mu. Now mu times what? Times, well, I've got a t here, so that's a 0. And I've got a t squared here, so that's a 0. So it's 0 plus 0 is e to the 0. E to the 0 is 1. Well, the conclusion didn't change. Now to find the second moment about the origin, I've got to take the second derivative of the moment generating function and evaluated at t equals 0. So here's the first derivative. Ignore the t equals 0 part. This is the first derivative of the moment generating function. And so we're going to have to differentiate again. And we're going to have to use the product rule to take the next derivative. And it is not difficult to do, but I'm going to let you do it. And when you finish that, you will have mu squared plus sigma squared. So that's the second moment about the origin. Now to find sigma squared is the second moment about the origin minus mu squared would be mu squared plus sigma squared. It's the second moment about the origin minus mu squareds add out, equal sigma squared. All right, so not real difficult, maybe an okay practice on taking derivatives, and a reminder of these theorems that we looked at are helpful to us, and they will help us solve problems easily. Do more or quit. I can't even find the cursor, so that might be a suggestion. It's time to quit. There it is. I got that much paper left. Okay, I'll tell you a couple things that you probably already know, but we've got normal distributions, and we will write x is normal. Now, mu sigma is sort of what you'll find the author of this current textbook using. Many other authors, and me included, use an uppercase N here for normal, but both of these notations are used. So x is a random variable that's normally distributed with parameters mu and sigma. Now, a normal 0, 1 is a standard normal, often called a z distribution. And the z distribution, and this really should be reviewed for you from Stat 374, 375. But if you need some reminding, just bear with me here. The standard normal distribution, there are some things that are distributed as the standard normal, like the results of modern bone density screenings are reported in a standard normal, a normal distribution with mean of 0 and standard deviation of 1. But this thing was enormously important in previous decades for calculating normal distributions that were not standard normal. And by that I mean that if x is normal mu sigma, then x, take a value of x, subtract the mean, and divide by the standard deviation, that's going to be normal 0, 1. It'll still be normal, but it will be normal with a mean of 0 and a standard deviation of 1. Now, why is that of fundamental importance? Well, what's the probability that x, and we'll take this x right here, is less than 3? That would be 1 upon sigma root 2 pi integral negative infinity to 3 e to the negative 1/2 x minus whatever the mean is divided by sigma squared dx. Now, I'm talking about in an age before computers. This would be extremely hard to evaluate. And in fact, you cannot find an antiderivative of this integrand. We'd call this the integrand, right? You can't find an antiderivative of that integrand and then use the fundamental theorem of calculus to just evaluate the antiderivative at the limits of integration and subtract and bingo, multiply by 1 over sigma 2 root 2 pi, and you got an answer. You'd have to use some numerical method, and there are numerous, but they're all computationally intensive, and we're talking about time before computers or even the little handheld calculators. No convenient computing machine available to most of us. So, boy, that was a hard problem. But a much easier problem would be to recognize that this probability is exactly the same as the probability that z is less than 3 minus whatever the mean is, this is the mu, divided by this value sigma. Now, why is that better? That's better because this z was widely tabulated. You could easily find a table of z, and this you would reduce to a number, and you'd look up the first digit here, and the second decimal point next 2 digits, and in the table there's your probability. And you didn't have to integrate hard things. So why didn't we do tables? Why didn't we do tables for this guy? Why do we have to do this z transformation? Well, because there's an infinite number of values that mu and sigma could have, and any of them could be interesting or important to us at any given time. And we can't make an infinite number of tables, but we can make a z table that would be convenient and widely available and accurate. And then we can just do this simple transformation, and I can look up anything that I need to know about the probability of x. I can calculate using just my little z table, one tiny table. And it really could be tiny, because some z tables you'll see, I think in the Triola book, for example, there's a z on the left-hand side. What do I mean by the left-hand side? Well, remember the z distribution would, oh man, what a crummy looking z distribution. Would kind of look like that. That would be 0, and this would be -1, and this would be +1. And we might have tabulated for different values along this axis and along this axis, the area to the left, maybe. But we really don't have to. If we would tabulate just this side, we could use the symmetry and we could find out anything we wanted to know about the other side. So the tables can be very compact, is the point I was getting at there. Now, today you've got a graphing calculator that'll calculate super conveniently any value of the normal distribution right from its own parameters, and you don't have to do the z transformation in order to calculate normal probabilities. The z still has some important things to tell us, and we still use the z, but not for the reasons that we used to use it a couple decades ago. So I do think that's where this needs to stop today. And if you've made it this far, I am hoping there was only a gap in the middle and that I'm still recording. And I thank you for having the patience to wade through this. So you have a good day, and there'll be more on the normal distribution coming up in 48 hours or so. So stop recording.